Our fourth and last simple differentiation rule tells us how we can differentiate things that are combined together with addition and subtraction. So this is called the sum and difference rule. It also works as nicely as possible. It says that the derivative of a sum or difference of two functions is the sum or difference of their derivatives. That sentence might not seem like it's saying very much, but it actually is saying quite a lot. In simples, what this says is if we're looking at the derivative of a sum or difference of two functions. So I'll write that as f of x, some stuff with x, and then plus or minus sum or difference of another function, another thing with x in it. So I'll use g of x for that. What this rule says is that this is equal to the sum or difference of the individual derivatives. So we can look at just the derivative of f of x. We can look at just the derivative of g of x, and then we will add or subtract them after we differentiate. One way that you could think about this is that the d dx, or the derivative operation, can kind of distribute here across plus and minus. We will see that this does not work for multiply or divide, but plus or minus, this is good. Here is the algebraic proof for this rule. If we define this big capital f of x as the sum of two other functions, f of x and g of x, and we form the limit definition of the derivative for the capital F of x function, then we will just substitute in x plus h into each of the functions here. Then minus f of x plus g of x, all divided by h. We can do a little bit of rearranging, put the g of x stuff together, put the f of x stuff together, and what we end up getting is two different limits that look like the derivatives of each of the individual parts. So we can differentiate the individual functions separately. Combining this rule with our other rules really allows us to differentiate any kind of polynomial now, because we can take powers of x and multiply them with numbers and then add or subtract them. That's the definition of a polynomial. And now we can differentiate any kind of polynomial given to us. So for example, let's find the derivative of f of x equals x to the fourth minus 3x squared plus 3x minus 7. What this rule says is that to differentiate this entire function, we can look at the individual pieces. So the derivative of x to the fourth will be 4x cubed. Then we have minus, that stays, this minus sign. We'll subtract the derivative of 3x squared. Well, that will be 3 times the derivative of x squared. Simple power rule tells us that the derivative of x squared will be 2x to the first. Then we keep this plus, and we add the derivative of 3x. That will be 3 times the derivative of x, which is 1. Then we subtract the derivative of just 7. Here we have a constant by itself, so its derivative will be 0. Now simplifying this gives us 4x to the third minus 6x plus 3. And here is the derivative of that polynomial. Again, if you like the d over dx notation, then what this says is if we take the derivative of the given function, we can split this up into finding the derivative of each of the individual parts. I've also used the constant multiple rule to take the 3 out of each of the second and third terms. Then we'll just find the derivative of each of the pieces. We get the same thing. If you like this notation, again, feel free to use it. I'm not going to use it very often because it's more important to understand the process, where if we have a minus, plus, minus in our minds, we can split this up and differentiate each part. But again, as we're learning, it's definitely okay to write things out this way. It can just get a little tedious at times, especially for this next example. So here we have a very long polynomial, y equals x to the eighth plus 12x to the fifth minus 4x to the fourth plus 10x cubed minus 6x plus 5. So what this rule says is that if we're going to find y prime, or dy dx, we'll differentiate each piece. Pause this video and see if you can find the derivative of this polynomial. The first term, x to the eighth, gives us 8x to the seventh. Then we will add 12 times the derivative of x to the fifth, which is 5x to the fourth. Then we'll subtract 4 times the derivative of x to the fourth, which is 4x to the third. Then we will add 10 times the derivative of x to the third, which is 3x squared. Subtract 6 times the derivative of x, which is 1, and then add the derivative of 5, which is 0. Taking at least one step of simplification here will give us 8x to the seventh plus 60x to the fourth minus 16x to the third plus 30x to the second minus 6. And here's the derivative of our initial function. Now you might be picking up on the pattern that when we have a constant multiple in front of a power, then what we end up doing when we differentiate is we bring the power and multiply it by the constant in the front. So 12 times 5x to the fourth, 12 times 5 gave us 60. If you see that, you don't have to write this intermediary step. You can go straight to here. Same thing with 4 times 4 gave us 16, and 3 times 10 gave us 30. In example 3, we have y equals 2 minus 3x times x plus 2. Now here we have a product of two things. We have not talked about how to find the derivative of a product of two things unless that product is a number times a variable to a power. We cannot just find the derivative of 2 minus 3x and then multiply it by the derivative of x plus 2. That's not a rule that we are told is true. In fact, we will have a way to differentiate products, but it's much more complicated than that. So what we'll have to do sometimes is use algebra to get rid of a product or maybe a quotient. In this case, the algebra to do is FOIL this out, multiply it out, distribute everything. When we do that, the first will give us 2x, the outer will give us plus 4, the inner will give us minus 3x squared, and the last will give us minus 6x. Just combining the terms together and maybe writing them in decreasing power will give us negative 3x squared minus 4x plus 4. Now this is something that we know how to find the derivative of. So go ahead and pause this video and make sure that you can differentiate a function that looks like this. We would write y prime or dy dx. Remember, those are equivalent. Just switching it up a little bit so that we get used to all of the different notations. Negative 3x squared, its derivative will be negative 3 times 2x. Then we'll subtract the derivative of 4x. That will be 4 times the derivative of x, which is 1. Then we add the derivative of 4 by itself, which is 0. Negative 3 times 2 is negative 6, and 4 times 1 is 4. So the derivative of this function is negative 6x minus 4. Note that if we did take the derivative of each part separately, meaning the derivative of 2 minus 3x, which would be 0 minus 3, and then the derivative of x plus 2, which would be 1 plus 0, and then we multiplied those together, we would get negative 3. And that is not the same as what we got here. And we kind of know that this is for sure correct. So what I'm trying to further iterate to you is that we cannot differentiate a product by taking the derivative of each of the factors. We have to either get rid of the product or use the product rule, which we will learn later. In examples 4, 5, and 6, we have 3 fractions. The numerators are the same in all 3, but the denominators are sort of different. In the first example, our denominator is a number or a constant. I know there's a radical there, but radical 5 is just a number a little bigger than 2. When this is the case, we can rewrite our function to look a little bit easier before we differentiate it. Dividing by a number is the same as multiplying by 1 over that number. So in other words, what we can write this as is 1 over the square root of 5 times 4x to the second plus 7x minus 5. The 1 over radical 5 is now a constant multiple. It's a number that we could write a decimal down for, but it's only an approximation unless we keep it with the radical. So this is, again, a constant multiple. So when we take the derivative of the entire function, What that means is that constant multiple, the 1 over the square root of 5, will stay and multiply by the derivative of this whole piece. So we will now differentiate 4x squared. So it'll be 4 times 2x. Then we'll add the derivative of 7x, which will be 7 times the derivative of x, which is 1. Then we subtract the derivative of 5, which is a constant all by itself, and so that's derivative is 0. Taking one step of simplification, we can rewrite the 1 over root 5 as still 1 over root 5, but 4 times 2x is 8x, and 7 times 1 is 7. So here's the derivative of that function. We could also write it back as a fraction, like 8x plus 7, all divided by radical 5. The function in example 5 is different in its denominator. Right here we don't have a constant down in the denominator, we have a variable. When this is the case, we cannot just take the derivative of the numerator, which would be 8x plus 7, and then put it over the derivative of the denominator, which would be 2x. This is not the derivative. We can't ever do this. We will have a rule called the quotient rule that will allow us to differentiate quotients where we've got variable up top and variable down in the bottom. But this one we can kind of get out of the fact that there's a quotient here. We can write this as 1 over x squared times 4x squared plus 7x minus 5. Now 1 over x squared is the same as x to the negative 2. Now we have a product of two things that involve variables, x to the negative 2 and then this polynomial. Remember that we also can't take the derivative of a product of two things by finding the derivative of each of the individual parts and then multiplying them. We have to get rid of this product. Well, the way to do that isn't too difficult in this case. We can just distribute the x to the negative 2 into the parentheses. What that will give us is 4x to the 0 plus 7x to the negative 1 minus 5x to the negative 2. Remember that these exponents are coming from adding the exponent in the negative 2 to the individual exponents that we're multiplying by. That's just an exponent rule. 4x to the 0, that's just 4. Then we'll have 4 plus 7x to the negative 1 minus 5x to the negative 2. Now this is something that we can now find the derivative of. Basically our goal is always to get numbers or numbers times x to a power, number times x to a power, only separated with plus and minus in between, with no variables being divided by each other or even multiplied. Now it's a good time to take the derivative of this. If we find g prime of x, we will take the derivative of 4, which is 0. Then we will add the derivative of 7x to the negative 1, which will be 7 times negative 1x to the negative 2. Then we will subtract the derivative of 5x to the negative 2, which will be 5 times the derivative of x to the negative 2, which will be negative 2x to the negative 3. Taking at least one step of simplification here will give us negative 7x to the negative 2 plus 10x to the negative 3. We generally don't want to leave negative exponents in our answers, so we can rewrite each of these terms here as fractions. So negative 7x to the negative 2 will be negative 7 over x to the positive 2, and 10x to the negative 3 will be 10 over x to the positive 3. And here is the derivative of the function that we were given. In example 6, we have a similar looking function to the one in example 5, except now in the bottom we don't have x squared, we have the square root of x. Okay, so we'll do the same sort of thing. We're going to want to bring this up and change this divide to multiply. So that will look like x to the negative 1/2 times 4x squared plus 7x minus 5. Then we have to get rid of this product, and again, that is easily done by distributing this x to the negative 1/2 into the three terms in the parentheses. Multiplying x to the negative 1/2 into 4x to the second will give us 4x to the 3/2. Then we will add 7x to the positive 1/2, and then subtract 5x to the negative 1/2. Here again is a good place to take the derivative now, because we have some pieces that we have rules that apply to. Please pause this video and see if you can find the derivative h prime of x. The derivative of 4x to the 3 halves will be 4 times the derivative of x to the 3 halves, which will be 3 halves x to the 1 half. Then we will add 7 times the derivative of x to the 1 half, which is 1 half x to the negative 1 half. Then we will subtract 5 times the derivative of x to the negative 1 half, which will be negative 1 half x to the negative 3 halves. Now let's just clean this up a little bit. 4 times 3 halves, we can cancel out the 2 in the denominator here with a 2 from the 4. That will give us 6x to the 1 half. 7 times 1 half, can't do much there except just maybe write that as 7 halves. And maybe we should bring that x to the negative 1 half down into the denominator. Then we will multiply 5 and negative 1 half, which will give us positive 5 halves. And then we can also bring that x down into the denominator and make its exponent positive. So in the end, we will have 6x to the 1 half plus 7 over 2x to the 1 half plus 5 over 2x to the 3 halves.